Welcome to Recording 1B in our series on Infinite Geometric Series for Unit 1, Chapter 1 of Mathematics 2200. Last recording, we developed the formula for the sum of an infinite geometric series, provided it met certain restrictions. Now we're going to focus on using the formula. As a reminder, here's the formula we developed last recording. The sum of an infinite number of terms of an infinite geometric series is equal to the first term divided by 1 minus the common ratio. Now we have to meet the condition though that the common ratio has to be between -1 and 1. Can't have a common ratio of 0 either. For which series can the formula be used out of these four? So if we look at this first one, the common ratio, they're all equal to 1/2. So we have r equals 1/2, and it meets the condition that -1 is less than 1/2, less than 1. It meets that condition up there and is not equal to 0. Therefore, we can use the formula. The next one, I'll leave it to you to show that r is equal to 1/2. Half divided by 1 is 1/2. You show that 1/4 divided by 1/2 is equal to 1/2 as well. Anyway, it meets the condition, so because it meets the condition, we can use the formula. For the next one, let's see what happens here. 1/8 divided by 1/16. That's equal to 1/8 times 16 over 1. 8 goes into 16 twice. Oh, that means the ratio would be 2. So even if the other ones work out to be 2, we still can't use the formula. If you check the other ratios as I've done, yes, it works out to be 2, but -1 is not less than 2 and less than 1. So therefore, that's false. We cannot use the formula. For the last one, we will get r equals -1/3. I'll leave it up to you to show that. So therefore, let's see, does it fit the condition? -1 less than -1/3, less than 1. That's true. That means we can use formula. All right, I've taken the three series we can use the formula for and put them over here on this slide. Let's actually find the sum. Before we do, I've jotted down some questions you should ask yourself before you attempt any of these questions. Always ask yourself, is the series infinite? Is it geometric? And does it meet the condition? Okay, and I just made a little correction there. R cannot be 0 as well. So in the first one, it's got an R value of 1/2, so it is geometric, it is infinite, and it meets the condition. So finding the sum of the infinite number of terms, term 1 is 400 over 1 minus 1/2. That's 400 divided by 1/2, which gives us 400 times 2, and we take the reciprocal of 1/2, which is 800. For the next one, S sub infinity is equal to term 1, which is 1, all over 1 minus 1/2 again. So I've got 1 over 1/2, multiplying by the reciprocal of 1/2. I got 1 times 2 over 1, which is just going to give us 2. Okay, in the last one, the series is infinite, it's geometric, and -1/3 is between -1 and 1. So if we go ahead and we find the sum, we've got S sub infinity equals term 1, which is 1 over 1 minus -1/3. So that's 1 over 1 plus 1/3, which is 1 over 4/3, which gives me 1 times 3/4, or just 3/4. To begin what should say example 2, not example 1, decimal 5/2 repeating has to be converted to an infinite geometric series and from there into a fraction. Now the repeating portion of a decimal is called its period. If we write this out in an expanded form instead of using the bar, we would have decimal 5/2, 5/2, 5/2, 5/2, 5/2, etc. So we can begin to separate this into other decimals. Decimal 5/2, that's the first period. The second period, 5/2, the 5 occurs 3 places after the decimal. So we have to start 3 places after the decimal for that one. Then the next one starts 5 places after the decimal, etc. Now we check for a common ratio. And indeed there is one. So our common ratio is decimal 0.1. So we ask ourselves the 3 questions. Is the series infinite? Yes, it is. Is it geometric? Yes, it is. And is this a true statement? Yes. So S sub infinity is equal to term 1 of this series, which is decimal 5/2 over 1 minus decimal 0.1, which gives us decimal 52 over decimal 99, which if we multiply the top and the bottom by 100, we will get 52 over 99. That's already in lowest terms, so we're done. In conclusion, our formula can only be used when the restrictions are met for that formula, and we can use that formula to convert a decimal value with a repeating pattern to exact fraction form.